here's the next group of VSEPR shapes that all kind of go together. They're based on 5 bonding regions around the central atom. So we're dealing with atoms that can take an extended octet. Now that may be a combination of bonding regions versus non-bonding electron regions, but all of these shapes have 5 total regions of electrons on the center atom. This first shape, the Trigonal Bipyramid, has 5 bonding regions. 4, 5. It's called a Trigonal Bipyramid because there's a triangle around the center. And then it's like a pyramid on top and a pyramid on bottom. So here are your 5 atoms. Around the center, those first 3 really are 120 degrees. And then you've got these guys that are 180. So that's why over at the front here it's got it listed as 180 and 120. The other angle that we could mark in, like from the center, either up or down, this would be 90. Those would really be 90-degree angles. So you really have to put on your visual thinking cap here, don't you? Trigonal Bipyramid. 3 around the center, 1 on top, 1 on bottom. And you have to know the bond angles too. Okay, so now make sure that you drew these Lewis structures right. Some of these are kind of tricky, and you really have to check the electron count to know that you have the structure right. You know, I wouldn't normally think of sulfur as taking 4 bonds, but he does. In sulfur tetrafluoride, my electron count was 34 electrons, so I plugged in the 4 fluorine atoms first. Fluorine has to have an octet. Sulfur is in the 3rd energy level, so he could take an extended. So with just the fluorines, that gave me 32 electrons. The extra pair goes on sulfur. So make a little note of this. We've got 5 regions of electrons, 4 bonding, and the 5th is this lone pair. So we're thinking about the original Trigonal Bipyramid structure, but one of the spots is not really an atom. One of those positions is the lone pair. So in your mind, and in class, we're going to feel the Trigonal Bipyramid. And to represent the lone pair, you're going to remove one of the atoms. Think about this. Remove atoms from the central triangle first. So in your mind, you're picturing this Trigonal Bipyramid. You're picturing a triangle in the center, and then 90 degrees up toward one, 90 degrees up toward another atom on the bottom. When you have to remove atoms to represent a lone pair, we remove them from the central triangle first. So do you see where that lone pair is, kind of tucked in on that ball and stick model? It's supposed to be around the central triangle. What you're left with is called a seesaw. Oh, cute. You could draw this a couple different ways. Like if they did ask you to draw a ball and stick model, you could kind of say, well, I'm going to have the central atom. And then you got, I'll make these, whatever the outer atoms are. You've got 2 that are 90 degrees. I should really say like 120 degrees. And then the other ones kind of form like the base of the seesaw. And then this would be like the ghost lone pair. Does that look like a seesaw? You remember ever being on a seesaw? So you've got like the 2 that are 120 around the center, up and down. And then if you remove one of the atoms from the central triangle, the other 2 are approximately 120. So if we mark in these, this guy to this guy, that's 180. And then around the central triangle, this guy to this guy, approximately 120. Slightly less than 120, because again, that negative electron pair takes up a little bit more space than a bonding region, so it kind of smushes the existing atoms. So you could either say slightly less than 120, or you could just say approximately 120. There's the seesaw. And again, like, it's kind of dangerous, because if you look at SF4 versus CF4, the formulas look really similar, but the shapes are not. CF4 with carbon in the center, that would be tetrahedron. That'd be a tetrahedron with all 109.5 degree bond angles. But with the sulfur in the center, you have a lone pair of electrons. It changes the shape. Now you've got the seesaw shape. And remember that too. Remove from the central triangle first, which is what happens in the next example. Weird structure, huh? Bromine trifluoride. Check your Lewis structures carefully, and you really have to check your electron count to make sure you have the right Lewis structure. Fluorine can only take an octet, but bromine can take an extended. And so with 28 electrons total, any extras go on the central bromine. So he does have an extended octet, which is okay. We've got 3 bonding regions of electrons. 1, 2, 3. And 2 lone pairs. So there's still a total of 5 electron regions around the central atom. But 2 of them are lone pairs. So again, you remove from the central triangle. So you kind of see where these guys came from. Here's one of the lone pairs. And here's the second. These lone pairs are coming from the central triangle. So if you remove one, you're left with this seesaw, which one time on an AP test somebody wrote the teeter-totter shape. Yeah, it does look like a teeter-totter. I get it. That's kind of cute. I laughed. If you have 2 electron regions around the center that are lone pairs, what you're left with is called T-shaped. You could kind of think of it looking like this. You got the central atom. You've still got your atoms that are 180 degrees. And then you've only got one left from the triangle. And so realistically, all these guys, like from here to here, these are both 90 degrees. And then obviously these guys are still 180. So in the front here, when it says T-shape, it lists 90 degree angles. And yeah, it's 90 degrees from like the top atom to the central atom or to the bottom atom. But then it is still 180 from top to bottom. So you could really say either. You could say, you know, there are some 180, or you could say there's one angle that's 180 and 2 angles that are 90. That'd be totally fine. So it makes sense why this is called a T-shape. So all I did from this original structure was just kind of give it a quarter turn. And then now here's where it looks a little bit more like a T. But it's essential that we understand that when you remove atoms to represent lone pairs, you have to remove from the central triangle when you're dealing with this trigonal bipyramid, when you're dealing with 5 regions of electrons. And so now check this last guy, iodine dichloride with a -1 charge. Yeah, yikes. So I added the electron count to 21, but the -1 charge means to add 1 electron for a total of 22. Now technically chlorine and iodine can both take extended octets. So if you have to make a decision, extra electrons go to the central atom. So any electrons that are extra go on the iodine. So iodine ends up with 5 bonding regions, or electron regions. There's 2. There's the other 3. 2 bonding regions and 3 lone pairs. So essentially what we've done to the structure is remove all the atoms from that central triangle. So here's a lone pair. This was a lone pair. And there's a lone pair. So everybody's gone from that central triangle. So do you see what you're left with is really just the atom on top and bottom. This is linear. It's true 180-degree bond angles. It's totally linear, no joke. So there are a couple different ways you could have a linear structure. You could really just have 2 bonding regions. And again, it could be single bonds, double bonds, triple bonds. Or you could have 2 bonding regions and 3 lone pairs. If we remove all 3 of those lone pairs around the center, or those atoms around the center, we replace them with lone pairs, what you're left with is just top and bottom linear. Perfect 180-degree angles. So do you kind of see now how it is so important that you can visualize this guy? You got to visualize the fiver, the trigonal bipyramid. If you draw any structure that has a total of 5 electron regions, it could be any combination of bonds versus lone pairs. In your mind, you have to think about this guy. If you try to just memorize these, you go crazy. You have to visualize this first structure, then visualize removing the 3 atoms around the center. If you remove 1, you're at the seesaw shape, where you've kind of got these 2 angled atoms in the center, and then you've still got top and bottom, the 180s. If you remove 2 around the center, you're left with the T shape. You got the 180 top and bottom, and then you just have 1 atom left around the center. And then finally, if you remove all 3 atoms around the central triangle and replace them with lone pairs, what you're left with is really just another form of linear, 180-degree angles.